Welcome to the class Computational Neuroscience, Neuronal Dynamics of Cognition. This week we'll talk about synaptic plasticity. So why is that interesting? Many of you have learned to ride a bike, and if you hop on a bike, you will remember how it works. All of you will remember the name of their mother. Most of you will remember the name of the US president in 2010. I remember very well when I first entered onto the EPFL campus, and you may remember when you came the first time on the campus of your university. But we don't remember everything forever. I don't want to remember where I parked my car on the supermarket parking lot 3 weeks ago. So, whatever we remember is stored in our brain. Our brain is made up of neurons. Neurons get active while we look at things, while we experience things. These neurons have long axonal branches, axons on this side, and they have dendrites. And if a signal arrives from one neuron, it will go over the synapse, the synaptic contact point on the dendrite, and it will cause a response. And this response can be measured. It has a certain amplitude. Now, synaptic plasticity means that when you learn new things, when something happens, then the response can change in size and it can become much bigger. So the amplitude of the response is a measure of the strength of the synaptic connection, a measure of the synaptic weight. What happens in biology if a weight changes? Well, I've turned around my image of the neuron, and now you see here the synapses again. So this is the part of the receiving neuron. This part is called the synaptic spine, and in there are ion channels. And nowadays, it is possible to record directly, to visualize directly the spine, the size of the synapse. And here is a small spine, and then it became a big spine, and remained a big spine. It remained a strong synapse for a very long time. Now, there are complicated biological processes involved in this. There are different polymerization and depolymerization of structural molecules. There are ion channels embedded in the membrane. There are hundreds of different molecules, and all these work together to make a strong synapse. They work together to change the synapse from a weak synapse to a strong synapse. What's the result of this? Well, globally, if you look at the brain, there might be more space for some people allocated to motor tasks. Motor sensitive areas are in this region here, and musicians who use their fingers a lot will have more space allocated to this than non-musicians. Now, a London taxi driver, for him it's a different part of the brain which is bigger, a part that's called hippocampus, and this part is involved in storing the map of the environment. Since a London taxi driver who drives through all parts of the city needs a good map of London, his hippocampus becomes larger than that of a bus driver who always drives along the same few streets. So the brain can adapt to the tasks, it can adapt to the environment, and synaptic plasticity is at the core of this. Synaptic plasticity should enable us to do different things, to adapt to the statistics of the task, to form receptive fields, allocate space, and similar things. Then we talked about memorizing names, memorizing episodes. That's also synaptic plasticity that makes this possible. We talked about riding a bike. Again, it's synaptic plasticity that's involved. So all this synaptic plasticity, all this is part of what we call learning. Now, at the same time, imagine now that a synapse got stronger. So the way I draw this here and later is that I draw a stronger weight, a stronger link for a stronger synapse. Now imagine some synapses got stronger, then it's easier for the activity of the brain to circulate between these neurons. And now this could happen that other synapses also get stronger, and yet other synapses get stronger, so that the whole brain blows up in activity, and this would end up in an epileptic state, a high activity state that has no functional meaning. So synaptic plasticity, yes, it should help us to learn, but it should also avoid blowing up of activity, and that means it has to control the state of the brain, and that process of control is called homeostasis. And synaptic plasticity should also be used to control the amount of energy used in the brain. So while this is sort of the specific parts that cause learning, these are more unspecific control mechanisms. So what's the program for this week? I will introduce the concept of Happian learning in various aspects. I will talk about experiments on synaptic plasticity. I will formulate mathematically the ideas of Happian learning. Then we'll see models of what's called spike timing dependent plasticity, and I will explain what this means. And finally, we'll go back to attractor memory models.